Hello dear students, welcome you all. Today we are going to solve section C of your question paper. Uh, you can see here, this is the section C, right? Section C of your question paper, and we will start solving from question number 5, question number 6, and then we will come to question number 7, right? Let's uh, go to the question number 5. The question was, the Fermi energy of potassium is 2.12 electron volt. Calculate the electron density. Clear? So it was a numerical problem based on the definition and expression of Fermi energy, right? So we know what was the expression for Fermi energy. First of all, we have to write down the expression for Fermi energy. It was, you know very well, Ef is equal to h square. No, sorry, it is h cut square. So we have to erase it. It is h square upon 2m bracket 3n upon 8 pi b, right, power 2 by 3. So this is the expression for Fermi energy. You can see here, here m is the mass of electron, n is the number of electrons, b is the volume of the given material, and again pi is a constant. So this is the expression we have derived in case of Fermi-Dirac statistics. In this expression, it is very clear that the Fermi energy depend upon the factor n upon b. Here n upon v is what? Electron concentration, we can say, or we can say free electron density, right? So it is the Fermi energy of any material, given material, is only a function of this factor because other things are constant. We can say the Fermi energy of any material is its inherent property that cannot be altered, changed, right? It depends upon the concentration of free electrons, or we can say concentration of valence electrons. Clear? So here we are asked to calculate this n upon V in case of potassium, and you are already given that the Fermi energy of potassium is 2.12 electron volt, right? What is the atomic number of potassium? Z is equal to 19. Clear? So now we will start solving this expression. Uh, we will start putting the value of here all the things so that we can arrive. So EF is equal to h square. H square upon 2m into 3n upon 8 pi b power 2 by 3. So if I rearrange this equation, then I will get n upon b is equal to 8 pi upon 3 into bracket 2m ef upon h square power 3 by 2. What I did, I simply took all these terms toward this side. Clear? 2mef upon h square power 2 by 3, and then I multiplied the rest of the things with this. Clear? You got this expression now. Now we have to put all the values here in this expression so that we can find the value of n upon v, right? So you are given all the values. N upon v is equal to now 8 into pi 3.14 divided by 3 into 2 into m. Mass of electron 9.1 into 10 raised to power minus 31 kilogram, right? Into Fermi energy is given 2.12 electron volt. So we have to convert this number into joule. So 1 electron volt, we know it is equal to 1.6 into 10 raised to power minus 19. Clear? Joule. Denominator, you have h square 6.62 into 10 raised to power minus 34 whole term square, and this whole term power here 3 by 2. Clear? So this is the next expression after putting all the values here in this equation, right? So when we will solve it, clear? This is the mathematics that you have to solve. You have to cancel certain numbers, certain powers will be get cancelled. So after solving it, you will arrive at 1.43 into 10 raised to power 28 per meter cube. So this is the answer to this question. You will arrive after solving this expression here. You can solve it. There is nothing difficult in it. First of all, you will solve the powers, this and this. So then after you will solve the other quantities involved in this expression, and then after you will arrive here. So it was a very simple numerical. It was simple only when we know what is the procedure to solve such kind of numericals, because it was going to use the expression for Fermi energy that is given here, right? So if anyone knows the expression for Fermi energy, then that person can solve this type of numericals, right? N upon V, concentration of electron, means number of electron per unit volume. So here you can see the answer is 1.43 into 10 raised to power 28 per meter cube. Means this much number of electrons are present in per unit volume of potassium, right? So this is the answer to this question. Clear? Now I am coming to the next question, that is compare three branches of statistics. Clear? So compare three branches of statistics. Compare three right. This was your next question. It was question number, I think, 6. Clear? So this question was discussed in the class many a times, that how we have to answer this question. So for answering this question, you can draw a table. This is the best way. You can draw a table here. Right. This is the best way to find the comparison, to do the comparison between three branches of statistics. This is, we know, uh, so this is Maxwell, Boltzmann, this is Bose, Einstein, and this is Fermi, Dirac. We know that we can divide the entire statistical physics into two branches. One is classical and other is a quantum. Clear? In quantum, we have two beings. Clear? Bose-Einstein statistics and Fermi Dirac statistics. So the first comparison between these three is the type of particle. Clear? So I have told you that in Maxwell-Boltzmann statistics, the particle are distinguishable. Whether they are identical or not, it doesn't matter, but particle are distinguishable. Even if the particle are identical, we can distinguish them in classical word. So the first comparison is distinguishability. Clear? Here the particle are distinguishable. Here the particle are not distinguishable. Particle are not distinguishable. I have told you that in quantum physics, when the particle are identical, then we cannot distinguish between them. If we have two electrons, we can't say which electron is electron number 1 and which electron is electron number 2. So this is the first difference, that here the particle are identical, distinguishable, but here the particle are identical and indistinguishable. We can't make them differentiate between them, right? In both the wings of statistics. The next difference that came here is the volume of the phase space cell. We know in case of classical statistics, the volume of the phase space cell is H naught cube. Here H naught can have any value, right? Even it can tends to 0, as small as possible. But in quantum statistics, the volume of the smallest cell, phase space cell, is H cube. Here H is the Planck's constant. So in this particular case, this value can't go below H cube. The volume of the phase space cell can't be less than this number, right? It will be always either equal to or greater than this number H. Here H is Planck's constant, right? So this is the second difference between these three wings of statistics, the volume of the phase space cell. Now the next difference is you can have in terms of number of particle entering in a phase space cell, right? So we know in case of classical statistics, there is no restriction. Any number of particle can go into a phase space cell, no restriction. Clear? Again, in case of Bose-Einstein statistics, we know that there is no restriction. Any number of bosons can go into a phase space cell. So there is no restriction. But here there is a restriction. Pauli's exclusion principle. Clear? So Pauli's exclusion principle make the restriction that only one particle can enter in a one phase space cell. This is very, very important. This difference is very important. There is no restriction. Any number of particle can enter into a given phase space cell. Any number of particle can enter into a given phase space cell, because bosons does not obey the Pauli's exclusion principle, whereas this wing of statistics follow the Pauli's exclusion principle, right? The next difference is this wing of statistics, Maxwell-Boltzmann statistics, it is applicable to gas molecules, right? We can say gas molecules. So molecules, right? Or other particle which are having dimensions greater than atomic dimensions, molecules, right? Or even greater than molecules. This Bose-Einstein statistics is applicable to bosons. Clear? Which particle are bosons? The very prominent example of a boson is a photon. Clear? Those particles which have either zero or a integral spin. I have told you in detail what is the concept of the spin. Clear? Spin angular momentum. Right? So this Fermi-Dirac statistics is applicable to which kind of particles? Fermions. Right? The prominent example is electron, proton, right? Neutron. All these are example of fermions, and these fermions have a half integral spin, 1 by 2 h cut, 3 by 2 h cut. I have explained in detail what is the reason behind it. Clear? So this is the next difference. Now, if I talk about the occupation index, Ni upon Gi, we have also derived the expression for all these three things of statistics. It is 1 upon e raised to power alpha plus beta e I. This is the occupation index. Your distribution law, we can say, in case of Maxwell-Boltzmann statistics. But if I go to this one, then it will become Ni upon Gi is equal to 1 upon e raised to power alpha plus beta ei minus 1. This is the difference. Here it will come minus 1. In this case, it will become 1 upon e raised to power alpha plus beta ei plus 1. Clear? So this is the difference between all these three things of statistics. Clear? So these are some important points which are mentioned in this table. The comparison, I made a 5 comparison. 4, this is 4 and this is 5. So you have to compare the three things of statistics based on this kind of comparison. This is the best way to compare the three things of statistics, that which type of particle are falling in which category, the volume of the phase space cell, restriction on the number of particle entering into a particular cell, which type of particle these are, like this is gas molecules, bosons, fermions, occupation index, right? Now, this is the difference between three wings of statistics. Here, n, if I talk about this Ni upon Gi, it gives us the number of particle Ni in that compartment. Gi is the number of cells in that compartment, and it depends upon these factors. Clear? So this is the answer to this question. So well, students, now I have answered the two questions of section C, question number 5 and question number 6, right? In the next lecture, I will solve the question number 7, last question of this question paper, right? It is starting from Bose-Einstein energy distribution law, drive Planck's law of black body radiation. So I will briefly discuss it in this lecture. That I was asking starting from Bose-Einstein distribution law. Now, when I have gone through your answer books, many students have derived Bose-Einstein distribution law. Again, the same mistake they have did in the case of here, question number 2. They have derived Maxwell-Boltzmann distribution law. So again, I'm repeating the same thing, that what is asked in the question paper. You focus on that. I have asked starting from, means you have to start from where? You have to start from that I have distribution law. You have to start from Bose-Einstein distribution law. This you have to start from here. You have not to drive this distribution law. This is already driven, right? And I am asking you to start from here and then drive Planck's law of black body radiation, right? So we will drive this expression in the next lecture, right? So thank you very much.